So today we want to consider current electricity. What actually is electric current? Electric current is simply the rate of flow of electric charges. And current is given as, like from the definition, rate of flow of electric charges. That is charge over time. Change in charge or change in time. Or you can just simply say charge over time. Understand that I means electric current and T is time and Q is the quantity of charge. So let's look at this example. For instance, a 20-coulomb charge flows through a conductor in 10 nanoseconds. Determine the current through the circuit. Okay? So what are we given here? We are given the charge, 20-coulomb charge. And we are given the time, 10 nanoseconds, that is 10 times 10 raised to the minus 9 seconds. So we can say I is Q over T, which is given as 20 over 10 times 10 raised to the power minus 9. So this will simply be 2 times 10 raised to the power 9. Ampere, that's the unit for current. Current density. This is the current flow in a conductor per unit area. And so current density is represented with J. It is equal to I current over area. It is measured in ampere per meter square. So let's take an example under this current density now. A current of 5 ampere flows through a conductor of cross-sectional area 2.0 millimeter square. Calculate the current density. So what are they given here? We are given the current, and that's 5 ampere. And then again, we are given the area, which is 2.0 millimeter square. We have to convert to meter square, divide by 1,000 square. This will give us 2 times 10 raised to the minus 6 meter square. So current density J is equal to I over A. The I is 5 over A. 2 times 10 raised to the power minus 6. And so here we would have 2.5 times 10 raised to the power 6 ampere per meter square. Drift velocity. You see, if you take a conductor that is not connected to any potential source or connected to an electric field, the electrons in those conductors moves randomly. But the moment the conductor is placed in an electric field or connected to a potential source, the electrons will move. And the velocity with which they move is called the drift velocity. So drift velocity is the average velocity of electrons in a conductor when an electric field is applied. And the drift velocity is given as current divided by area times number of electrons, or you say number of charge carriers, because electrons are the charge carrier, times the charge on an electron, which is 1.6 times 10 raised to the minus 19 coulomb. It's also important to note that we've done what we call current density. That current density J is equal to I over A. If we put that here, we mean we are replacing this I over A with J. We can also add that drift velocity can be just J over N, number of electrons, times the charge on an electron. So let's take examples on this now. So let's look at this example now. Example 3. Calculate the drift velocity of free electrons in a copper wire of cross-sectional area 1.0 millimeter square when the current flowing through the wire is 2.0 ampere. Take the number of free electrons in copper as 1 times 10 raised to the 29 per meter cube. So to solve this, the first thing we do is to write out our given. We are given firstly the area here, and that is 1.0 millimeter square. So I will divide this by 1,000 square, and that will give me 1 times 10 raised to the minus 6 meter square. Then next, we are given the current here, I, to be 2.0 ampere. And again, we are given our N to be 1 times 10 raised to the power 29 per meter cube. Okay, now to solve for the drift velocity, we know that the drift velocity is equal to I over A n times charge on electron. So we have it that charge on electron is given as 1.6 times 10 raised to the power minus 19 coulomb. So this will simply be 2.0 over area 1 times 10 raised to the power minus 6, then times number of charge carriers or number of electrons. We are given that to be 1 times 10 raised to the power 29 per meter cube. That's the number of electrons per volume. Then times per meter cube, not of putting the per meter cube, times charge on electron, 1.6 times 10 raised to the power minus 19. So if we evaluate this, 1.25 times 10 raised to the power minus 4 meter per seconds. So this will give us 1.875 times 10 raised to the power minus 4 meter per seconds. Electrical resistance. The electrical resistance of a conductor is a measure of the opposition to the flow of electric current through that conductor. It is measured in ohms and it varies from one conductor to another. There are 4 factors that affect the resistance of a conductor. The first is the length of the conductor, the second is the cross-sectional area, the third is the type or nature of the material of the conductor, and the last one is temperature. So the resistance of a conductor is directly proportional to the length of the conductor, meaning that as resistance increases, as the length increases, the resistance would increase, or as the length reduces, the resistance would reduce or decrease. For the cross-sectional area, the resistance of a conductor is inversely proportional to the cross-sectional area of the conductor, meaning that if the cross-sectional area reduces, resistance would increase, and if the cross-sectional area reduces, resistance would increase, or if the cross-sectional area increases, resistance will reduce. That's what inversely proportional means. Now the third one is the nature of the material. This is summed up to be called resistivity of the material. So different materials have different resistivity actually. So that's about that. And the resistance of a conductor is just directly proportional to the resistivity of the material. So combine this first, second, and third factor together. We have that resistance of a conductor is equal to resistivity of the material times length of the material conductor over area of the conductor. And lastly is the temperature. If temperature is increased, the resistance of a conductor actually increases, and if temperature is reduced, resistance actually reduces. But the effect of temperature on a conductor will be studied later. So let's look at our first example now. Example 1. The resistance of a wire of length 20 cm and diameter 3.0 cm is 10 ohms. Calculate A, resistivity of the wire, B, the conductivity of the wire. So let's take this question now. First of all, we are given the length of the wire. The length is 20 cm. So divided by 100, this will become 0.2 meter. Again, we are given the diameter 3.0 cm. So divided by 100 now, that gives us 0.03 meters. And lastly, we are given the resistance to be 10 ohms. Okay? Now, we are required to get firstly the resistivity. So to get resistivity, we need area. So let's go and get area first. Area is pi d square over 4. And that will be pi times diameter is 0.03 square divided by 4. This will give us 7.07 times 10 raised to the power minus 4 meter square. Okay, so now we know that resistivity is equal to resistance is equal to resistivity times length over area. Hence, we can say resistivity is equal to area times resistance over length. And this will give us the area to be 7.07 times 10 raised to the power minus 4, then times, the next one is the resistance, which is 10, all over the length, which is 0.2. So this will give us 0.035 ohm meter. The next one we have to get is the conductivity. To get the B, which is the conductivity, is equal to 1 over resistivity, which is 1 over 0.035. And this will give us 28.57 per ohm per meter. Example 2, a thin film resistor is made up of NECO and of thickness 1 micrometer. So, first of all, the thickness is the length actually, 1 micrometer, and that's 1 times 10 raised to the power minus 6 meters. Calculate the resistance between the opposite edges of such a film of area 1 millimeter square. So, we are given the resistivity, firstly, also as 10 raised to the power minus 6 ohm meter. So we calculate the resistance between the opposite edges of a film, if the area. So the area is given as 1 millimeter square, which is 1 times 10 raised to the power minus 6 meters square. So all we just need to do here is to say the resistance that we're looking for is equal to resistivity times length over area. And so the resistivity we are given as 10 raised to the power minus 6 times the length, 1 times 10 raised to the power minus 6 over the area, 1 times 10 raised to the power minus 6. This eliminates this. So the resistance is 10 raised to the power minus 6 ohms. Ohm's law. Ohm's law states that the current flowing through a metallic conductor is directly proportional to the potential difference across its ends, provided that temperature and other physical factors are kept constant. So the potential difference of the voltage is directly proportional to current, or current directly proportional to voltage. All are the same actually. And so the V is equal to, when we put a constant of proportionality, which is the R, we change this to equal to. And so this is the Ohm's law actually. This is Ohm's law. V equal to IR. Where V is the potential difference and I is the current in ampere. R is resistance in ohms. So let's take this first question now. A current of 2 milliampere flows in a TV. So we are giving the current 2 milliampere, which is 2 times 10 raised to the power minus 3 ampere, flows in a TV of resistance R. When a PD of 4 volts is connected, you are giving the voltage 4 volts. What are the values of the resistance and conductance? So we are looking for R. We know that V is equal to IR. Hence, R will be equal to V over I. And this is 4 divided by 2 times 10 raised to the power minus 3. This will be 2 times 10 raised to the power 3 ohms. Then lastly, the conductance. Okay? So, number 2, conductance. Conductance. Represented with G. It's just 1 over resistance. So that's 1 over 2 times 10 raised to the power 3. This will give us 5 times 10 raised to the power minus 4 Siemens. So we want to look at parallel and series connection of resistors. Let's take the first one now, resistors in series. If we have resistors in series as shown in the circuits above, we have the total resistance will be R1, which is the resistance of the first resistor, plus R2, which is the resistance of the second resistor, plus R3, resistance of the third resistor. Even if they are 10, you keep adding them in such manner. That's how to get the total resistance. So RT here means total resistance. Now, I want you to know about this kind of connection is that the current across each resistor is exactly the same. And that's the current flowing in the circuit. If the current flowing here is 2 ampere, that's the current across this, that's the current across this, that's the current across this. but the voltage across them are not the same, except if they have same resistance. If not, the voltage across each of the resistors varies. Okay, so that's that about this. Now let's take example 1. 3 resistors of resistance 8 ohms, 6 ohms, and 10 ohm are connected in series. Calculate their total resistance. At times we call it effective resistance. The same thing actually. So our given now, we are given R1 to be 8 ohms. We are given R2 to be 6 ohms. And we are given R3 to be 10 ohms. So we can say total resistance is equal to R1 plus R2 plus R3. And that will be 8 plus 6 plus 10. And that will simply give us 24 ohms. That's that about this. Resistors connected in parallel now. Now, if resistors are connected in parallel, they probably look very similar to this. This is how the basic connection should look like. Now, it's important to know that the total resistance of this circuit will be given as 1 over total resistance is equal to 1 over R1, that's the resistance of the first resistor, over 1 over R2, the resistance of the second resistor, plus 1 over R3, resistance of the third resistor. Now, it's also important for you to note that the potential difference across each resistor is the same, and the current flowing in each resistor is not actually the same, except if their resistance is the same. So you see, the voltage here is exactly the same as the voltage here, and that's the same voltage here, that's the same voltage here. So voltage across the 3 resistors are the same, but the current divides across each of them, except when their resistance actually is the same. So let's take this question now. 4 resistors of resistance 10 ohms, 5 ohms, 3 ohms, and 4 ohms respectively are connected in parallel. Calculate the value of the combined resistance. So we have 4 resistors here. So we have R1, which is 10 ohms, and we have R2, which is 5 ohms. We have R3, which is 3 ohms, and we have R4, which is 4 ohms. Okay, so now 1 over total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. 1 over, our R1 here is 10 plus 1 over R2 is 5 plus 1 over R3 is 3 plus 1 over 4. So we take our LCM now. LCM of 10, 5, 3, and 4. Okay? Let's quickly do that. Ten, 5, 3, and 4. So 2 can go here, that's 5. This remains 5, 3, and 2. So 2 can go again, 5, 5, 3, and 1. So times 3 and 5 again. So 5, 5, 1, 1, and then 5. So this is 60. So 10 is 60. 6 times 1, that's 6. Plus 5 in 60, 12 times 1, that's 12. Plus 3 in 60, that's 20 times 1, that's 20. Plus 4 in 60, that will give us 15. Times 1, that's 15. So this will give us 12 plus 20 plus 6, 28, 38. 38 plus 15, that's 53. It is 53 over 60. I need to confirm again. This 18, 38. That's 53. So this is 1 over R total. So I'll quickly turn this. That's R total now over 1 is equal to 60 over 53. So this is our total resistance actually for this question. Example 3. 3 resistors with values 20 ohm, 30 ohm, and 60 ohm are connected in parallel, and the combination is connected in series with a 10 ohm resistor across a 50 volt battery. Find the potential difference across the 10 ohm resistor and B, the parallel circuit. Let's draw out this circuit now. So we have 3 resistors in parallel first of all. It's going to look like this. And then so this is it now. We have 20 ohms, 30 ohms, and 60 ohms. Now this combination is connected in series to another resistor whose value is 10 ohms. And then connected to a 50 volt supply. This is how the circuit diagram looks like. Okay, so that's that. Now, the first thing we need to do is to find the total resistance of this parallel combination, this parallel circuit. So for the parallel circuit, For the parallel circuit, 1 over R total will be equal to 1 over 20 plus 1 over 30 plus 1 over 60. For this, the SCM is 60. 60. 20 in 60 is 3. 3 times 1 is 3. Plus 30 in 60 is 2. 2 times 1 is 2. Plus 60 in 60 is 1 times 1, that's 1. Is equal to 1 over R total. So 1 over R total is equal to 6 over 60. You can revert this. RT over 1 will be equal to 60 over 6, which is 10 ohms. So our R total is 10 ohms for the parallel combination. Now, if everything here is 10 ohms, that 10 ohms will be in series with this. It's going to look somewhat like this. This is 10, everything here 10 ohms. Now connected on that 10 ohms here. And this one now connected to the 50 volt battery. So this is how it looks like. So for the entire circuit, the total resistance, let me say sum of resistance, let me just use this symbol, is equal to 10 plus 10, because that is in series, and that will give us 20 ohms. If you've gotten the total resistance of the entire circuit, we cannot go ahead to calculate the current in the circuit, but we need the current in the circuit to answer these questions. So what will be the current in the circuit? We have the relationship that Ohm's law says V is equal to I R. So we can say I is equal to V over R. In this case now, V over what will cost our sum of R actually. So what is our V? V given here is 50 volts. That's what we're giving in this question. 50 over total resistance, that's 20. So this will give us 2.5 ampere. What now we've gotten our current. Now, the first thing we're asked to get here now is the current or the potential difference, V across the 10 ohm resistor. So V across 10 ohm resistor. What's it going to be? It's going to be I in the circuit times the 10 ohm itself. So that will be, the I is 2.5, that is I in the circuit, current in the circuit, times 10, that's 25 volts. For the second one, for the parallel connection, voltage is PD across the parallel circuit. Is you see the I times the resistance of the parallel. So we've got the total resistance of the parallel. And that is, we did it here, that will go to be 10 ohms. So it's going to be I, which is 2.5 times 10, and that's 25 volt as well.